Let's talk about a specific clustering algorithm called hard k-means. First, let's define the problem. Given a set of observations, x1 through xn, where xi is d-dimensional real vector, so we're in Euclidean space, if you want to say, like, if you want to think that way. The problem is we want to partition all of those n observations into k clusters such that k is less than or equal to n. So there is enough samples to be put into clusters. And those are the subset partitions such that the set or the sets minimize the within cluster Euclidean square distance. So we want the average Euclidean within cluster Euclidean distance to be minimal. So take the mean or centroid point, the mean point in k-means algorithm in the clustering usually called centroid, and take all of the points assigned to this cluster, compute within cluster distances, and the average or the total sum of those distances across the classes should be minimal. Seems easy, but in general, this is an NP-hard problem. It's a combinatorial problem because you can have multiple assignments, uh, like multiple subsets, and it's a discrete combinatorial problem. Hard assignment. What do you assign to one cluster? What do you assign to another? And we don't want to work or deal with the uh, combinatorial problems usually and p-hard problems especially. So usually we resort or fall back to heuristic solutions. And two heuristic solutions that we will be considering in this class, today's lecture and the next lecture, is k-means algorithm and Gaussian mixture models. We already discussed and considered Gaussian mixture models as a generative forward problem, but we will talk about how to actually estimate the Gaussian mixture model in the next lecture. In this lecture, let's figure out how to tackle this NP-hard problem by another approach. So let's try to manually simulate k-means, how it will work. So k-means algorithm works in the following way. Given the data, those blue points, the diamond shape, guess random means for each of the clusters. Say we already set a hyperparameter that there will be 3 clusters. We guess that they will be in those random locations. Then we assigned points to the nearest cluster center. So we assume that our guesses are the means of the new clusters or centroids, and we assigned whatever is closest to K1, we assigned to cluster 1, whatever is closest to K2, among all of the 3, we assigned to cluster 2, and we did the same for K3. That's step 2. Then in the third step, we took our assigned points and recomputed, updated the mean. That was our first original guess, but now we recomputed the mean. What is the mean of the new assignment? And we updated our cluster centroid. That's a step in the clustering one subpoint of iterative process. So we re-estimated the mean using assignments from the means using assignments from the last step. Now let's reassign our points again based on the same um, rule. Whatever is closest to the new means um, or mean estimates get assigned to that particular cluster. Like as you see, our previous assignment was green for K1, but now once the mean shifted, the Voronoi uh, bounds or the Voronoi cells have also been updated, and then this green point moved into cluster 2, this red point and this green point moved into clusters 3. Well, but now, after we've done that, we are ready to update the means again. With this new cluster assignments, we will re-estimate cluster means using assignment of the last step. And we will continue this process until convergence when we cannot make any more reassignments. And consequentially, when that happens, we cannot move the means either because they're already at the average locations. So just to drive the point back home, let's look yet at another example due to David McKay. This is our data that we're working with. So we start with random locations of the means, and as you see, we've done this assignment. Well, I'm sure there's a line here. The border, the Voronoi cells must be linear, so everything here closest to this mean was assigned to one cluster, to the diamond cluster, and everything closer to that mean was assigned to the plus cluster. Then we took all of the pluses, compute the average, and moved our original estimate of the mean to the average. We've done the same with the diamonds. And the assignment and continued until convergence. Assignment, update, assignment, update, assignment, update sequence converges, and in fact, it provably converges. It doesn't converge to a local optimum, but in fact, that it is convergent, you can observe by the process that we're following here. Our objective, our potential function here is remember the interclass distances averaged, and every time those distances are minimized, so every time this functional is decreased, because when every time we do reassignments, we assign closer and closer points to the means, or we shift the means so that uh, the points become closer. So this functional is always reduced, and there is sort of a plug proof that this is a dynamical map, and if we can find this physical notion, potential function, I believe, for the system, then what is it? Well, it's like an energy function. If we imagine that those distances are springs where there's stiffnesses, then by Hooke's law, this describes as uh, the tension, the tension in the springs. And every time we reassign, we loosen that tension, minimize this tension. So eventually will converge because this energy function is called basically Lyapunov function. And for the dynamical system, if that function exists, that means the dynamical map converges. That's an intuition of how the proof might have gone. But I just ask you to trust me on that. The process always convergent, but we'll see how it converges incorrectly sometimes. Or how it can. So once again, reiterate the complete algorithm. All we need as an input is data plus desired number of clusters and plus distance metric. Distance metric will define the space our data lives in. The distance metric defined here on the screen is just practically Euclidean distance, uh, sum of the square of the differences, so mean squared error. But you can use any other metric if you want to. K-means will work. You can use even, I don't know, Earth mover distance, or any other more or less interesting metric. Pearson correlation as a similarity can be made into a metric, and you can use it to L1 distance would be fine as well. So then initialization is the only step. There's randomly pick centers of the K clusters. Then iteration proceeds as follows. First, decide the class membership of n objects by assigning them to the nearest cluster center. Second, re-estimate K cluster centers, centroids, or means by assuming the membership found above as correct. And when do we terminate? We will terminate if none of n objects change membership in the last iteration. If something changed, we keep repeating those iterations. Let's look closer at each of the important parts of our assignment update cycle of the internal in the iterations. So assignment happens in the following way. We decide the class membership of n objects by assigning them to the nearest cluster center. Basically, for nth sample, the class membership is argmean of the distance to the already estimated mean from that sample. For convenience, although it may look complicated right now, but it will help us to deal with even more complicated problems and to generalize the algorithm, let's define the responsibilities. So if we have four clusters, a responsibility vector is a binary vector of four elements, and such that all elements are zero, but that element, that single element in this vector, for which our point assignment is defined. That our point in question x sub n, if it is assigned or belongs to cluster K, then it's non-zero. So responsibilities of clusters, remember Gaussian mixture model, responsibility for generating that point. And this in k-means, in hard k-means, those responsibilities are binary and they're hard. Only one of the clusters is responsible for this point, or equivalently, only the point is assigned to a single cluster at a time. But we can see now that if we take all of our points from the first one to the last one and put n by k matrix, it's a binary matrix, and each column will only have one single non-zero element because each sample can only belong to one class. And then next slide will become clearer if you keep in mind this rectangular matrix. So what if there is a tie that the point is right on the decision boundary? Where do we assign it? Well, in a continuous space, this is very rare, But if that happens, just assign the point to the smallest matching k. Basically, pick some random or arbitrary rule to break ties. So another um, sub step subs yeah sub step of our iteration is update. Now we have all of our assignments, responsibilities. What do we do with them? So now we re-estimate the K cluster centers. We move our means or centroids. Look what happens. We sum all of our elements with corresponding weights. Um, so what that means is index is K. We are computing the mean K. What happens here is that we multiply by an indicator, by a responsibility, which is either 0 or 1. So if this sample was not assigned to cluster K or to the mean K, to centroid K, then this responsibility is 0. So think about our K by N matrix. So each sample is either assigned or not assigned. So when um, we are talking about this kth cluster, kth mean, we're talking about summing along this dimension. So this Rk is exactly the count of numbers of elements that were assigned to this class. As you can see, we are summing along this row and we're computing capital R sub k. But here, all we're doing, we're multiplying each of those elements as weights times to the corresponding x sub k sub n vectors. This is a matrix of responsibilities. Our x sub n matrix is somewhere else separately. So, for example, if our x n's can be organized into D by N matrix, so where each column here is our sample X, or each individual sample N, then we can multiply by the row of this matrix, and we will obtain the mean, K-mean. And what the row of this matrix will do, because of responsibility matrix will do, since those are binary, it will only pick those columns that correspond to non-zero elements of the responsibilities and sum them up. Then we'll need to normalize by R still, and we'll get mu sub k. That is the update step. Um, just to reiterate what is happening, we're starting with any random choice for mean 1, mean 2, and mean 3 in this 3 mean example from Duda and Hart, their famous pattern classification book. And once we're doing update after update, as you see here with 1, 2, 3, the Voronoi tessellations keep shifting until they shift into the right position, and thus we partition the place. So the space, partitioning the space means um, separating the space into non-overlapping regions such that the union of those regions gives us back the complete space again. So k-means algorithm partitions the space continuously as each iteration progresses. So how fast is the k-means algorithm? And what is computational complexity? Well, computing distance between each of n objects and k clusters is of order k times n linear. You have to look at each point and the distance to the mean. Sounds fantastic. Linear is not exponential, but when you're dealing with internet scale data, even linear is a problem. So people have invented a lot of nearest neighbor searches and data structures such that so that you can um, solve this problem easier. Uh, but in general, it like every easy problem when magnified to scales becomes difficult or impossible even depending on the scale. So next step, computing cluster centroids. So just averaging each object. Each object belongs to at least some cluster, so it gets added once. That's why the big O of n, uh, the complexity is of order n of this iteration. And then for L iterations, the total complexity, since our distance complexity is larger, is L times K times N. So is it guaranteed to terminate? Yes, it's guaranteed to terminate, as I explained already. Let's see an example of dependence on the starting position. Imagine we don't know anything about our data. We don't want to make any recommendations about starting positions. We just allowing algorithm to blindly start and do something. Throw 3 points. We know there are three clusters. We don't know where they are. Throw 3 points as initial starting position, two green, one red, and then when it converges, look what happens. This is a perfect k-means result. It converged, and it's from the point of view if k-means is correct. Everything that is closer to the green is at the green. Sure where this line will be. Somewhere just in between those two and just in between those two, since we are only considering the shortest distance. Not a bad, at least remember, clustering is subjective, and this is what k-means will give you. But if we ask a random person from the street, they will probably say, "Oh no, those should be the clusters." Uh, why is that? We don't know what's going on in the head of those random people in the street, but I guess they have a way or a reason to think this particular image clusters the way the cyan color delineates it here. K-means thinks otherwise. So what else can k-means do to us if we give it three different random seeds? This is our previous example data set, or the same as before, and we're initializing four means and running to convergence, and look what it converged to. This is called one cluster, this is another. So maybe visually we would think that there are three clusters there, but k-means based on just the Voronoi tessellation does not necessarily optimize our visual or intuitive notion of clustering, right? It only is based on the distance. Second run gives us quite another clustering where most of the data belong to the largest cluster and the others are sharing a smaller subcluster. So um, that's an example of what do we optimize when we iterate and solve k-means algorithm. Well, we spoke about it before. This is the objective, the intercluster. Actually, we'll minimize intra-cluster distance or average intra-cluster. So within the cluster, we want our points to be as close to the centroid as possible among all of the possible configurations. And of course, it's very hard. The problem is NP hard to guarantee that we will arrive to the optimal solution, but we are trying and arriving to a solution. In the worst case, k-means on moderate data sets is so fast that we may be able to simply restart it with a few random restarts. And if we have a ways to somehow visualize our data and just make an expert opinion whether it works or not, the result that k-means obtained for us, then it's ideal. We can run multiple times and just take a look and decide what to do with it. But how to choose the number of clusters for k-means? Can we choose the number of clusters automatically? No. And again, just a little mantra that I keep repeating, and the mantra is there is no um, hyperparameter free learning. So there is a hyperparameter that we need to somehow set, and this is number of clusters. So one of the heuristics is called elbow method of k-means clustering. Take our objective function that we minimize, intra-cluster distance, average intra-cluster distance, and keep increasing the number of clusters and computing this, running k-means and computing this metric. That's what we're plotting on the y-axis here, and this is a decaying feed. So we are getting better and better, continuously better, the more clusters we add. That's in general a problem of the likelihood and problem of metrics like that, that the more parameter, it's kind of like an overfitting problem. The more parameters you have, the better you can feed the data. So the more you add, the better is your feed. When to stop? For k-means, the stop is recommended to do at the elbow. If you have this inflection point in your graph, choose your number of clusters right at the inflection point. It is a heuristic, and we have that done that once. It works or can work, but imagine difficult situations when it would not work. Where is that elbow in this graph when everything is sort of linearly decaying? I don't know. Very hard to choose. So the more smooth this is, the less we can do. Um, because we cannot find the elbow criterion. Let's consider a couple of failure modes of k-means. So one failure mode of k-means is when we have a dense lump of the data, like lots and lots and lots of very similar objects, and then we have a large diverse cluster that is kind of non-circular. When this situation arises, we are able to estimate the smaller cluster, but because all we care is equidistant, um, sum of unrelated points get assigned to this cluster. Although if we were plot the distribution based on the density of the samples, this samples would be having very low probability of belonging to that class, whereas because of the high variance here, these samples have high chance of being assigned or belong to this um, group, to this cluster. That was one failure mode. Another failure mode is what if our data is not grouping and centralizing, lumping into circular clusters? Well, always k-means has a tendency or um, what's the word I'm looking for? Um, it has a tendency of splitting horizontally because that's when the distances are easier minimized. It's very hard to find this solution. It's unlikely, but a solution like that is more likely than solution of this when narrow the uh, nearby clusters get separated right through. Its K-means is blind to the clustering and densities, so it prefers solutions on the right. So another problem besides those couple failure modes, another problem is borderline points. Let's look at one of the examples. Well, but even here, let's look at these examples. They are assigned to this cluster now, but they're so far away from it. Yet when we compute the mean, they are computed with equal contribution as the rest of the points, and they have the same effect, even though they may be noisy because they're right on the boundary, they're near the opposing cluster, near the other cluster, and still they're counted as the same weight as the every other sample. And this is a problem which we will shortly solve.